Okay. Um, just to repeat a lot of the same information I've already put on the board. Again, be sure that you make up that your 8 by 11 front and back sheet that you can use on Friday for the test, and also you'll be able to use one for the final exam. I am going to be finishing formulating the final exam tomorrow. I can tell you this, it's equally weighted among all 4 units. So that means that first, and as I was looking back at that first unit, I'm thinking, oh my God, it seems like a year ago that we covered this stuff, all right? I'm going to be just writing up a sheet of what I call some recommendations on how to formulate your sheet. And I'll be handing that out on Friday, okay? So hopefully that'll help. Again, the final exam will just be slightly modified problems from the 4 tests, okay? So, and then I'll be grading this test on Friday, over the weekend, so that you can have them back on Monday, all right? And the take-home quiz is due Friday. Is there any questions, concerns? I see something here. And you want both the sheets? Yeah, Jerry, I do. Have them put their name on the sheet and tuck it in to their text, okay? All right. Okay. So where we are here is we're finishing up the last part of section 16.6, and we're talking about calculating surface area, or put it this way, calculating the area of a surface. And there are basically 2 cases here. Case 1 and case 2. Now, case 1, we'll go over this first. So 2 cases. And each case has a little bit different formula connected with it, okay? Now, the first case is where the surface is given by a parameterization, which is what we've been talking about, and where we have a 3-dimensional vector, I, J, and K, with parameters, and so the surface is described that way. So this is the case where the surface is given by a parameterization. And what we're talking about is R, say U comma V, those are our parameters, equaling some function x of uv times the I vector, plus some function y of uv times the j vector, plus some function z of uv times the k vector, okay? All right. And u and v vary in some 2-dimensional domain that we generally call capital D. All right. Now in this case, okay, this is how our surface is given, and let's call capital F the surface that is covered just one time as U and V vary throughout the domain D. So what I'm saying here is we don't want to paint the surface twice. We just will cover it one time as our parameters go through this domain. All right. So this is the formula. Put an asterisk here by this. The surface area, let's call it capital A of S, that's this little shorthand. Well, what it equals is the double integral over that domain D of the following. We take our two tangents here up to our surface, R with respect to U, R with respect to B, and we calculate a dot product, a cross product, which gives us another vector. Okay, a cross product gives us a vector, and then we calculate the magnitude of that vector. And that is what gets integrated over our area. So RU is here's our surface. So RU is the partial derivative of the first component with respect to U times the vector I. The partial derivative of the second component, again with respect to U, times the vector J, plus the partial derivative of the third component, again with respect to U, times the vector K. And RV is similarly described, except now we do the partial derivatives with respect to V instead of U. So that's dx dv times the I vector, dy dv times the j vector, plus dz dv times the k vector. Okay. So we have to calculate those two vectors, and then our cross product, that gives us a vector, and then we calculate the magnitude which, remember, is the square root of the square of the individual components. All right. And then we do the derivative. Then we do the antiderivative. All right. So let's look at a specific example here of this. Okay. Example. So here's let's see, which one do I want to do here? I've got all kinds of examples. I think I'll do this one here. Find the area of the surface given with the parametric equations x equals u squared, y is equal to u times v, and z is equal to 1/2 v squared. So u and v are our parameters, and let's see, we're going to say that where u goes from 0 to 1, u goes 0 to 1, and v goes from 0 to 2. All right. So this is our domain, capital D, right there. Now, this is a little bit different than how we've been giving it before, but it's really actually the same thing. Note that our surface, R of uv, can be given this way. Okay, here is our x function, u squared, and that's times the I vector, plus our y function, uv, times the j vector, plus our z function, 1/2 v squared, times the k vector. Okay, it's just initially given a little bit different format by giving it as these three equations, parametric equations. Okay, so the first thing we have to do here is we have to calculate R with respect to U and R with respect to V. And that shouldn't be any great problem, I hope, with this. So let's look at R with respect to U. U is our variable, And so u squared is our first component, so that derivative is going to be 2u. And now I'm going to write it in the bracket format. So that's our first component, 2u. Second component, we have u times v, but v is a constant, so when we do the derivative with respect to u, all we have left is the v. And then the third component is 1/2 v squared. Well, v is a constant, so that derivative is going to be 0. Okay? And now let's get our v. And so now the first component is u squared. Well, now this time that's a constant, so this first component is going to be 0. Second component is u times v. Well, now u is our constant, v is our variable, so that's going to be u. And then the third one is 1/2 v squared. Do that derivative, and we get v. Okay. All right. So we got that far. Now we have to do the cross product. So remember with this, we set up that 3x3 matrix. Across the top, we put I, J, and K. And then let's put RU next, 2U, V, and 0. And then RV, 0, U, and V. And calculate the determinant. Okay. Again, we're going to go across this first row to do that. So we start out with the I vector, and we cross out the first row in the first column and get the determinant of what's left. And that's going to be v squared minus 0. So that's going to be v squared. Okay. Then we go to our second component in the first row, and please remember we put a minus sign in front of the j. And now we cross out, again, the first row, but now the second column, and get the determinant of what's left, and that's going to be 2u times v minus 0. So that's 2uv. And then we go to the last component, k, and cross out, again, the first row, but now the third column, and get the determinant, and that looks like 2u squared. All right. So if that's another a little bit shorter way that I can write this then is my first component is v squared. Be careful with the second component. Don't forget the minus sign that's in front. So that's going to be minus 2uv. And my third component is 2u squared. All right. So that's the cross product. Now, once we have the cross product, then what we have to do is we have to calculate its magnitude, right? So let's see what we get here. So we have to calculate, we're going to have the square root of the square of each of the components. So the first component is v squared, and we square that, and we get v to the fourth power. The second component is minus 2uv. We square that. That gives us a positive 4u squared v squared. Be careful with the algebra. And the third component is 2u squared. We square that, and we get 4u to the fourth power. All right? So this is, going back to our formula here, this magnitude here, this is what we're going to be taking the double integral of. So let's put my double integral here over d dA. All right. Now let's remember what d is. D is where u goes from 0 to 1, and v goes from 0 to 2. Okay. All right, now looking at this thing, and hopefully you're going to figure out that we're not being too unkind here, that actually this does that inside that square root, that's really the square of an expression, all right? So can anybody figure out what this is the square of? Yeah. V squared plus, and then we have 2u squared, and that all thing is squared. And if you FOIL it out, you'll realize that that is the case. So therefore, we're taking the square root of a square. Everything is positive on the inside, so that's good. So this thing then can now be rewritten as double integral over d, square root of a square, so I'm left with v squared plus 2u squared. Hopefully very simple integrand to get, and then that's dA. Okay, so we know with these double integrals, or triples for that matter, what we have to do is now get it as an iterated integral, okay? Right now as an iterated integral. Okay, so let's see. It really doesn't matter in this case which one I start with. I don't think there's any advantage much one way or the other. I think I'll just start on the inside with u. So u goes from 0 to 1. And then I have v squared plus 2u squared, and that'll be du. And then my outer integral I'll have as my v, where v goes from 0 to 2, and that'll be my outer integral. Okay. All right. Okay, so, how about writing the 1 there? All right, so now we just do the antiderivative, first of all, on the inside, work from the inside out. Okay, so that on the inside, u is our variable and v is our constant. So the antiderivative of v squared is going to be v squared times u. And the antiderivative of 2u squared is going to be 2u to the third over 3. So 2/3 u to the third power. And let's put our bracket, and we're going to evaluate that from u equals 0 to u equals 1. And then let's put our outside integral 0 to 2 dv. Okay. This should all be familiar territory. So let's see, the top one, u is equal to 1. So that's going to be v squared plus 2/3, right? And the bottom of, when u is equal to 0, both of the terms are 0. So that's nice. So now we have the single integral of v squared plus 2/3. Do that with respect to v. We have v to the third over 3 plus 2/3 times v. Evaluated now from 0 to 2. So we have 2 to the third, that's 8/3 plus 2 times 4/3. And then it's minus 0. So we end up with what? 12/3, which is 4. Okay. All right. And any question on that one? I do have another example, which I don't think I'm going to go through, because for starters, it's not bad until we get down to, the devil's always in the details when you get down to the final calculating the antiderivative. And it's one of those things that we've seen, but it's not something that, unless you're some kind of idiot savant, that you would remember. Okay. It actually involves, I'll just put it up here, just not the whole thing, but just put this one integral involved. The second thing involves calculating from 0 to 1 of the square root of 1 plus u squared du as part of its calculation. And you think, well, gee, it doesn't look very complicated. However, it's a mess. It actually, you can, well, the nice thing to do is, of course, to put it in a computer, A second way to do it is look in an integral table, and an integral table will give you the antiderivative of this. Or the way that I approached it is I did a I started the trig substitution, and when we have a 1 plus like this, you would want u equal to the tangent, say, of theta, all right? So what you get here is 1 plus u squared, then is 1 plus the tangent squared of theta. Yeah, right. Okay, and so 1 plus the tangent squared, let's see. Right, 1 plus the tangent squared is equal to the secant squared, right? Okay, and then du, well, the derivative of the tangent is the secant squared. So we have that. And so what we have here, now this is then the square root of 1 plus u squared, which is the square root of the secant squared. So what we end up having here then is this gives us a secant, this gives us a secant squared. So we have secant cubed d theta, all right? And I think maybe you have a vague memory. I think I actually did this one in class, and it involved integration by parts. And you have to then flip one side of it over to, and all that good stuff. And of course, then if we're going to keep it like this, remember, if I do a change in variable, if I'm going to keep it in that variable, I do need to change my limits of integration. So let's just, and then I'm going to stop with this. So when u is equal to 0, the tangent, what would the tangent of theta would be equal to 0. So what would our theta be equal to? What tangent gives you a 0? Okay, tangent is what? Sine over cosine. Where does sine give you a 0? At 0, right? Okay. So that would be theta equals 0 would be our lower limit. And then the top, when we have u is equal to 1, so we'd have 1 equals the tangent of theta. What would our upper tangent be? Pi over 4, right? Right. Okay. So and then I just thought, well, no, we're just not. I mean, it's fine. Here's actually the nice, for those of you who are interested, there's the nice complicated formula for the square antiderivative of 1 plus u squared is this whole thing right here. Right, I know. So it's that's a little bit too much for this time of year, okay? So anyway, that's my example with the first case where the surface is given as a parameterization. All right, so be sure you know how to apply the formula that I asterisked. Now the second case is where the surface is given as a nice, simple equation. Second case. Surface is given as z equals some function of x and y. All right. So we've seen this kind of thing before. X, y, and z. As x and y vary, z varies, and we end up with some kind of surface floating around. Okay. So this is the case where the surface is given in this format, z, instead of a parameterization with the 3 components, it's just given as this type of thing. All right, so in this case, then, the surface area of z equaling fxy over a region capital D is, okay, again, let me put asterisk here. Surface area is, again, it's a double integral over D. But now what we're going to have on the inside, there's a lot less preliminary calculation that has to be done. There were about 3 different steps we had to do, or a couple different steps we had to do with the first one. This one is just going to be the square root of 1 plus the derivative of z with respect to x squared plus the derivative of z with respect to y squared under the square root, dA. All right. So be sure that you note that formula down. And then let's look at an example involving this case. Okay, so say, okay, I'm actually going to do 2 with this one. Let me do this one first. Okay. Find the area of the part of the plane, and here's the equation of the plane, 3x plus 2y plus z equaling 6, that lies in the first octant. Okay, let's remember that octant, that first octant, that's where x is bigger than 0, bigger than or equal to 0, y is bigger than or equal to 0, and z is bigger than or equal to 0. That's the first octant. Okay. Okay. So that's the problem. Now, in this case, one of the things we have to do here is, well, we want to figure out which type of problem it is. Is this a case 1 or a case 2? Can it be written as a case 2? Yeah. I can very easily isolate the z on one side of the equation, and I have case 2. So just isolate z, so subtract, so z is equal to minus 3x minus 2y plus 6, and we have case 2. All right. I guess while I'm at it, let's figure out, we know we have to figure out the partial derivative, which is pretty easy. Partial derivative with respect to x is going to just be minus 3. The partial with respect to y is just going to be minus 2. That's easy. But another thing, the hardest part of this problem is figuring out properly your domain D. That's the hardest part. Because you're not handed it on a plate. Okay. So the thing is, the domain, this domain, this is going to occur strictly on the xy plane. All right. It's where x, it's the area that x is going through and y is going over. Okay. So it's just going to be on the xy plane. Now on the xy plane, so it's strictly going to be in here somewhere, okay, on the xy plane. For any point on the xy plane, what's the value of z? The value of z is 0. So z is equal to 0 on that plane. All right, so let's take this. So let's plug in 0 for z, and let's see what we get here, okay? So we get 0 is equal to minus 3x minus 2y plus 6, and this is going to give us the equation of a straight line. All right? So we know that that is going to be one of our boundaries here, okay, because that's where this plane here, going out, and it goes out, it's going up, it's going down, it's crossing this XY plane. So where it crosses that XY plane, that's going to be one of our boundaries for this region that X and Y vary over. So therefore, this straight line is one of our boundaries. Now, we also know that this is in the first octant, so we know that X is also bigger than or equal to 0, and Y is bigger than or equal to 0. So we have all these boundaries here, and so we can figure out what D is. All right. So now let's figure out what D is. So D is strictly on the XY plane. So I just do a two-dimensional graph here. And now let's figure out this straight line here. We've got, that's one of our boundaries. I think that what I'm going to do with this thing is put Y over, I like to just put Y over on one side. So let's add 2Y to both sides. So I get 2Y is equal to minus 3X plus 6. And then I'm just going to divide by 2 to get it in the MX plus B format. So Y is equal to minus 3 half X plus 3. So this is our MX plus B format. All right. So from that, we know that the y-intercept is going to be 3. So right up here, it's going to go there. And then we know that its slope is negative 3 halves. So it's going to go down 3 and then over 2. So it's going to hit the x-axis at 2. So our line is going to be like this right here. Okay? Now, so that's part of the boundary. We also know that x is bigger than 0, y is bigger than 0. So this triangle right here, that is our D that we're integrating over. Right. Does anybody have any questions about how I found that? We're only looking at x, y here, so that we set z equal to 0. Okay. So let's set up our integral here. So we know that the formula is that double integral over D. Again, I'll just rewrite the formula here for this case. It's 1 plus derivative of z with respect to x squared plus derivative of z with respect to y squared dA. But nice thing in this case is that we found that both of those partial derivatives are just numbers. So this is the integral over D of the square root of 1 plus, well, dz dx was negative 3, so I square it, that gives me 9. dz dy was negative 2, I square it, and I get 4 dA. All right. So under the square root, we just have what, the square root of 14. Of 15? It's 14. Okay. My arithmetic can be shaky at times, but I think I got this one nailed. All right. Now, there's actually now a clever way to do this and just a regular way to do it. So let me show you the clever way to do this. Okay, all we're integrating is some kind of number, so I can certainly bring that number all the way out in front. So we have the square root of 14 times the double integral over D times 1 times dA. Now, this right here, this is the formula for the area. When you just have a 1 there, that's the formula for the area of the D. And in this case, our D is a nice triangle. our triangle D. So the area of a triangle from primary middle school is what? 1/2 base times height. 1/2 times base times height, right? So therefore the area of the triangle, and that's our D, is 1/2. Our base is what? 2 units. Our height is 3 units. So that comes to a 3. So very quickly, if we're just real clever, we can then say that our answer correctly is 3 times that square root of 14. All right? Now let's suppose we just don't quite pick up on that, and we just go on the usual way. So let's just put this as the not so clever way, but it'll still work. All right, so let's take this here, and I'm just bringing that square root of 14 out. And now remember, if we're going to evaluate this double integral, we have to write it as an iterated integral. Okay, so let's see here. Let's go to my drawing here. Okay, so what would, now we could go either way with this. Now this, let me write the equation, this line, the equation of that line is y is equal to minus 3/2 x plus 6. Since I already have that written out like that, what I would do is first integrate it then this way with respect to y, and then do the x. Yeah. Oh, thank you. Yes. All right. Okay. So let's see. Let's do my inside one. Then it's going to be the bottom y is 0. My top y is minus 3/2 x plus 3. And then and that's dy, and then my x goes from 0 to 2. Okay, like that. All right. So let's see, let's figure out the integral. Well, basically, the antiderivative here, that's really a 1 there. We're talking about y, and it's going from 0 to minus 3/2 x plus 3, and then my outer integral is 0 to 2 dx. So that inside one is just going to end up being minus 3/2 x plus 3. And then I have my outer 0 to 2 dx, and then we go from there. So this antiderivative is minus 3, let's see, x squared over 2, so it'll be minus 3/4 x squared, and then plus 3x. Okay, and then that's from 0 to 2. And let's see what we get here. So this would be minus 3/4 times 2 squared is 4, plus 3 times 2 is 6. The bottom ones are 0. So that's going to be minus 3 plus 6. So it's the same answer, 3. And then, oh, don't forget, on the front here, I've got that square root of 14 that's multiplying everything. So we have the square root of 14. Okay, same answer. All right. Let me do one more with the second case, and then we'll take a break. And then the last part of class, I just can either, if you have some concerns about the take-home quiz, or I can do we can work over a couple things from the review set. All right. Where is it? Okay, there it is. Okay, second example. Okay, find the area of the part of the paraboloid And I tell you, with these names, I still have to think again as to exactly what that is. All right. Part of the paraboloid, okay, here they'll give you the equation here. Z is equal to x squared plus y squared. That lies under the plane Z is equal to 9. So this is a little bit reminiscent of, in the wording of some of those problems that you had in that last test, in the last unit. I mean, just the wording of it, okay? It's very helpful here to draw a picture, all right? Because one thing we have to figure out here is we have to figure out, again, like with the first example, is we have to figure out what D is. And again, D is going to be on the XY plane. That's what X and Y vary over. Okay, so first of all, this paraboloid thing, actually that's the X squared plus Y squared is a circle. It's just going to be something that comes out like this. Everything around is going to be a perfect circle. So it just kind of goes up, and this is a nice perfect circle there. So that's roughly what it looks like. All right. And then it gets topped off that lies under the plane. So right up here, say when Z is equal to 9, we've got a plane here that goes across where the Z value is equal to 9. So that plane would be certainly parallel to the XY plane. All right. Now, this thing, let's see, its equation is Z is equal to X squared plus Y squared. Then it hits that plane Z equals 9. And that's all we're interested in. So we have to figure out what we're talking about here, down here on the XY plane. So how might I figure that out? We're going projecting. We're doing like a shadow projection down. We're trying to look at some area down here. How do I figure that out? Right. You're going to set them equal to each other. You find where they cross each other's paths. Okay. So you just set 9 equal to x squared plus y squared. And that's going to be the area on the xy plane. Now this, of course, is a circle around the origin. And what's the radius? The radius is 3, not 9, it's 3. So down here, we're talking about a circle radius 3. So that's our D. All right. So now you're thinking, oh, this is looking like we're going to be working with polar coordinates, and that's exactly what we're going to be working with. Okay. So, here's our general formula here. Double integral over D. Again, that's square root of 1 plus dz dx squared plus dz dy squared dA. So, of course, we haven't figured out dz dx, but that's easy. Dz dx here is going to be 2x. Dz dy is going to be 2y. So this is going to be the square root of 1 plus, that's going to be 2x in parentheses squared, so that's going to be 4x squared. Dz dy squared is going to be 4y squared dA. Okay. So this just screams out for polar coordinates. All right. So we're going to use polar coordinates to evaluate this. Okay. So with polar coordinates, how can I represent that square root? Right. 1 plus 4r squared. Right. So this is going to be the square root of 1 plus 4r squared. Because remember, r squared is equal to x squared plus y squared. All right. And then, of course, now remember we have our r, dr, d theta, okay, that we got to tack on. And then let's figure out our bounds here. Well, for starters, this goes all the way around, so d theta is going from 0 to 2 pi. And then r here, this is a circle of radius 3, so r goes from 0 to 3. Okay. And I think at this point it should become a fairly routine antiderivative and to get. Notice one thing we can do off the bat, since all these are numbers, I can separate just to make life a little easier. So 0 to 2 pi times d theta times then the 0 to 3 square root of 1 plus 4r squared r dr. I can do that right off the bat. And then for the second integral, I just need to use a standard u substitution where I'm going to let u equal 1 plus 4r squared and go from there. Du then is going to equal 8r dr. So this r dr is going to be 1/8 times du. In fact, I'm just going to, since there's a definite integral with numbers, I'm just going to do the entire thing in the new variable. So I'm going to go on right now and switch my limits of integration. So when r is equal to 0, u is equal to 1. Now when r is equal to 3, u is equal to 1 plus 4. Now that's r squared, so that's 9. So that's 1 plus 36. So u is equal to 37 as our upper limit. So this becomes a limit from 1 to 37. And let's see here, r dr gets replaced by 1/8 du. And then the square root is just replaced by u to the 1/2 power. And then this thing here, what does that evaluate to without going any further with that? That's just 2 pi. All right. And then this one is going to be 1/8. U is going to be to the 3/2 power, but we're going to be multiplying by the reciprocal 2/3. We have 2 pi in front. And then we evaluate from 1 to 37. Let's simplify this as a 1/4 times 3. So it's 2 pi times 1/12. And then it's going to be, the top one is going to be 37 to the 3/2 power minus 1/12 times 1 to the 3/2 power, which is just 1. And of course I can simplify, I can cross out a factor of 2. If this 37 to the 3/2 is fine like this, or if I wanted to, I could write it like 37 times the square root of 37, and that would be that problem, okay? Question on that one? The polar coordinates, be able to recognize when those help you out. Okay, why don't we take a 5-minute break then? This stuff is, my goodness, nobody is here from Eureka. Not a single little soul is here from Eureka today. I think they're having, I think they might be having some kind of senior something or another going on, I guess. A senior skip day. More like a senior banquet or something like that. So, right. Yeah, I mean, I have a lot of high school students in my algebra class, and several of them were missing this morning. Yeah. Yes, sir. A present? 2. 2 presents. Oh, I am blessed. Thank you. I got you. Have a great. Got it. Bye. Jerry, are you there by yourself, or are your students having some kind of senior event today? Because nobody's here from Eureka. And maybe she's not really there either. I don't know if she's still there. She may have left. She's there, but maybe she's not there. Okay. Did you get your test back yet? Oh, you got to take one test.
Then you get to the practice final, the same final in the game. So he's giving you a practice final, which is reading. Right. Same question. I'm not feeling so bad. About the not being given. That's maybe 10 hours. So the rest of the short fall. Have you looked over the test, by the way? In a little bit. It's like, it is, it's like, yeah, I don't think so, but, yeah, I need to do it. Does he provide you with a solution to that? I think that's what from black one, but I don't know how to bring that up. That's not fair enough.
Well, first of all, is there anything involving the take-home quiz that's of any pressing concern? Oh, yeah. Mm-hmm. Right. Something that you just can't figure out at all. Oh, okay. That's not good to hear, Jenna. But you have an answer. So that's
Figure out 2 problems.
all right. What have you got?
Number 1 and 2.
Because those are the only ones that you've looked at so far?
No, I did the rest.
Oh, you did the rest of them. All right.
Well, great. Conservative, so I thought it has to be conservative. But we The number 3.
No, it doesn't have, no. It does not have to be conservative for you to determine what that integral is. It's just nice that it's conservative because then you have that little f function that you can figure out, and you can then just plug that in, the endpoint minus the other endpoint, and you get a quick answer. But for that, you have to follow the formula there for this.
Yeah, that's what it is.
Right, but it certainly can be evaluated. That one's probably one of the more difficult ones. So you're talking about 1 or 2? 1 and 2? Well, let's look at number 1. So what number 1 is involving here is evaluating this integral x ds. Okay. So let's see. What do we have here? We have to get this parameterized, right? What is c? C is the arc of the parabola. Y equals x squared from 0, 0 to 1, 1. So this is just what we're talking about here. The parabola from 0, 0, then we just go up to 1, 1, and we stop right there. So it's that little thing right there. Okay, that's our C. Okay, so what do we have to do with this kind of thing first? Don't we have to understand what our parameterization is of the curve? So we're already told that y is equal to x squared. Now a curve only has one parameter. We've been usually using the letter t for it, because but you could use the letter x for it. That's fine. So if y is parameterized as x squared, but how is x parameterized as?
Square y.
No, you only have one parameter. In this case, it's going to be x. You're not going to make it into the square root of y. X is just going to be parameterized as itself. That's it. X equal to x. Simplest parameterization you can get. All right? And this is where x, now what is our range of our parameters here? X goes from what to what? 0 to 1. Okay? All right? So we now have to get this, we have to get this in terms of the parameterization. All right. So x here, well, x is just parameterized as itself. X. All right, that's it. We okay with that? I mean, that's just that simple. How do we figure out this ds? dx as in Sam. Okay, isn't this going to be from a to b of our function in terms of the parameterization? How do they label that in the book? Do they say r of t? And we have to parameterize our function, and we're going to end up with a dt, or in this case, it's going to be a dx. All right. So what do we have here? ds is basically the Pythagorean theorem, really. ds is the length of your curve. It has two components, really, dx and dy, right? So this is going to be dx dt squared plus dy dt squared. Or I should put x here because we're using x, all right? dx squared plus dy dx squared, all under the square root. So certainly, in preparation for Friday, let's see, this is from section 16.2. Where are you? Okay. You certainly would want to, right at the bottom of page 1087, there's this formula very much like this, all right? Formula for right at the bottom of page 1087. I'm sure that if you look back in your notes that I had an asterisk by this formula, all right? And so that's the formula that you'd have to use. So part of the game, part of the game with any of this is the danger with just writing down formulas is, okay, you can have every formula that we've ever had written down on your paper, but if you don't know when or how they are applied, those you might as well just have nothing on your paper, all right? Because that will mean nothing to you. All right. So let's look at this, though. So therefore, this is going to be now, a to b is going to be 0 to 1. Our function is, with relation to the parameterization, just stays x. Now, this will be times, well, dx squared, that's going to be a 1 squared or 1. Now, what's dy dx squared? First of all, what's dy dx? 2x, right? So we need to square that because y is equal to x squared, so dy dx is 2x. We square that, and that's what, 4x squared. And then we have our dx. And this is similar to the problem that we just worked, where you do a u substitution, and you will work the problem. Okay, and I won't go any further with that. All right, but that's setting it up. The second problem, then, is a little bit different because in the second problem, we're not doing ds, we're doing dx and dy. So the second problem is integrate over c, y to the third dx plus x squared dy. And again, we have this parabola business. X is equal to 1 minus y squared as we're going from 0 minus 1 to the point 0, 1. All right. So basically, this is the same as, let's see, when x is 0, we're going to have y is either going to be plus 1 or minus 1. All right. And then when y is 0, x is 1. So isn't this thing going to look like this one? When x is 0, y is either plus or minus 1. So isn't this part of the curve going to be looking like this? Yeah. All right. Okay, so it's a similar kind of deal. Now this time, x is parameterized as 1 minus y squared. So how will y be parameterized?
Y equals Y.
Yeah, y equals y. And then, so y is our parameter. And what are the numbers between which y varies? Negative 1 and 1. Minus 1 less than y, less than or equal to positive 1. All right? So we set this up, again, with our parameterization minus 1 to 1. Now, what do we have here? This is what? Y to the third. Okay? Okay, well, y is just parameterized as y. So y to the third is just going to be parameterized as y to the third, okay? Now, this thing here is basically, we have to replace this. Okay, we're given that x is equal to 1 minus y squared. Okay, y is our parameter. We need to replace the dx in terms of dy, because y is our parameter. So I'm going to, just like you do when you do substitution, right? This dx is going to be replaced by what? Do the derivative of the other side, which is going to be negative 2y, and then we tack on the dy. So I'm going to replace, because we are taking, this integral is with respect to y. So I replace that dx, let's put a parenthesis, minus 2y times dy, like that, with that. And now we have the second part of this, x squared. Now x is parameterized as 1 minus y squared, so I have to put that in terms of our parameterization. So in parentheses, I put 1 minus y squared, and I square that, so I'll FOIL that out, square that. And now dy is just going to stay as dy. And then you go and evaluate that. Okay? So in this case, and again, the formula is here, it's knowing how to apply it. And I know, again, I've put an asterisk by it, but this one would be the types of formulas that we see number 7, what's written as number 7 on page 1090. But again, I covered that in the notes, so you should see that in your notes. All right. Okay. Is there anything else? I'm going to go with Jordan here. Yeah, Jordan.
Item number 6, are we supposed to determine how
Okay. So we're talking about number 6 here on the take-home quiz. All right. Okay. Well, let's look at number 5 first and number 6. And the question that Jordan has is first of all, the question is figure out whether the vector field is conservative or not. All right. So notice that number 5 is a two-dimensional case because number 5 is they're both three-dimensional, right? So forget that. Okay, three-dimensional for both of them. So the way we figure out that a three-dimensional vector field is conservative is to calculate its curl. Figure out the curl of that vector field that you are given, and if the curl ends up equaling the 0 vector, then F, our field, is conservative. So let's do this one and so it's the same process. Let's do this with number 6. Okay, first of all, yes?
I found this, like an equation in the book that's like the dp over dy equals.
That's for 2 dimensions.
But there's 3 of them. If they all equal each other, then it's conservative. There's 3 different ones. So they're all equal.
Okay, this is from the textbook, and is it for 2 dimensions?
No, for 3.
No, it's for 3. So, no, for 3, we use the curl. For 2 dimensions, here, let's just do this as an aside here. If it's a 2-dimensional field,
Right.
you understand the difference between a 2-dimensional field and a...
But I just found something for all 3 of them.
That's for all 3 of them.
There's all 3 of these.
Oh, okay, I see. Yeah, and that's all related to the curl.
Those
All right. Let's see. Let me check here in the, that's gonna be, that's 16, 5. Oh, yeah. Right. DP, wait a minute, did you, hold it. Okay, PQR. So you've got PZ equaling RX, QX equaling PY, and, okay, and QZ equaling, okay, yeah, that's equivalent to what we're doing.
Okay.
That's fine. Okay. All right. Okay, so since you're able to bring a note with you, because see, the reason for the curl is because that's hard to remember, all right? But this is what Jen is talking about for three-dimensional case. In fact, this is found on page 1115 of the book. And so if we basically have this, if our field is represented as P, Q, and R, we've got the three components of our field. If we look at the partial of the third one with respect to Y, if that equals the partial of the second one with respect to Z, and we have three things here, then if the partial of the first one with respect to Z is equal to the partial of the third one with respect to X, and then finally, if the partial of the second one with respect to X is equal to the partial of the first one with respect to Y, then it's conservative. That's actually the same in a different way. That's the same thing as the curl being zero vector. All right. So that's fine. All right. I'm just used to doing it as the curl, but that'll work. That's fine. Well, I'll do one of these curl things, but Jordan, do you understand that for 3 dimensions, that's what you're going to have to look at? All right. Let me just figure out for number 6, let's just look at this. Let's just figure out the curl of F. In number 6, F is what? E to the Y, X, E to the Y, plus E to the Z, and then Y, E to the Z. All right. So let's do so the curl is I, J, and K. And then, let's see. Remember, the second thing we put in this is the delta, delta X, delta, delta Y, delta, delta Z. And then finally, we put our vector E to the Y, X, E to the Y, plus E to the Z, Y, E to the Z, like that. And we do our determinant, and it gives you the same kind of thing. So we can go across like this and figure this out. I think it's I'm not even going to figure it out. It's so simple. Let's not worry about it. So let's say it does equal the zero vector when you do all those partial derivatives and subtract. Now the thing is, okay, we found out, let's go back to number 6 here. So we figured out that it's conservative, and they tell you to use this to evaluate this line integral. Okay, so can anybody tell me, okay, we figured out it's conservative. How can we use it to figure out this line integral? Integral of C S dot dr, where C is a line between the points 0, 2, 0, and 4, 0, 3. Okay, easily. What do we have to find? We have to find that little f. It's actually called the potential function. So to do this, we have to find little f such that our force field is equal to the gradient of that little f. And then it'll be easy to calculate the integral. So the way that I like to do it is this. Okay, here's our three components. The first one is little f with respect to x, and that equals ey. The second component is little f with respect to y, and that equals x e to the y plus e to the z. Our third one is little f with respect to z, and that equals y e to the z. And then you do those partial integrals. Okay, so the first one, basically, f, do the integral with respect to x of both sides. And y and z are constant. So my antiderivative here is going to be e to the y times x. Y is constant. But we could have an additional function of the variables that are considered constant. A g of y, z could be hanging on to that. And this is our little f function. But we have to do all three. So now we do the middle one with respect to y. So we take the antiderivative of x e to the y plus e to the z with respect to y. Now x and z are constant for this one. So the first one's going to be what? X e to the y is just going to be x e to the y. And then e to the z is going to be what? Y times e to the z, because e to the z is a constant. This is our little f, except we could have tacked onto this some function h of x and z that are treated as constants. Okay, we're 2/3 of the way there. Now we have to do the third one. And so the antiderivative of f of z with respect to z, and that's the antiderivative of y e to the z with respect to z. Okay, and that antiderivative y and x are constant, so that's y e to the z, plus some other function perhaps of x and y. All right, and that's also equal to f. So we then make sure, we then compare, we have three things that are equal to our little f function. We just match things up. So we see that we've got to have x times e to the y, x times e to the y, that has to be there. Also, y e to the z has to be there. And then that's it, plus a constant. So just by matching it up, we have our little f is x e to the y plus y e to the z, plus some constant k, but we just let that equal to 0. Yeah?
Is the k just what becomes of all the constants here now?
Well, the thing is, yeah, whenever we do an antiderivative, we at least always have a plus constant, right? So that's what this represents. Yeah. But we're just going to say it equals 0. Because when we plug it in, it's going to cancel itself out. So this is our function little f. So basically, because it's conservative, this is equal to little f. Now our endpoint is what? 403, evaluated at 403, minus little f evaluated at 020. All right, so now it becomes very simple, hopefully, to do. And so, let's see, for 403, what do we end up getting here? A is just going to be a 0. For this one, what value do we get when we plug in 4, 0, and 3? Now we just get 4 minus And now let's plug in 0 to 0. Minus 2. So our answer is 2. Right. Okay. All right. I was going to look at a Green's theorem from the review set. And I think I'd like to look at the review set. So this is section 16.4. This is listed as problem number 5 from page 1114. So this involves Green's theorem. So what do we have here? We're told to evaluate the line integral c of x y squared dx plus 2x squared y dy. This is number 5. This is problem number 5 under section 16.4 here on your review set from page 1114. Let's see. So this is number 5. Number 5, page 1114. And let's see where let's put where, let's see, D is the region enclosed, I'm going to write it like this, by from x going from 0 to 2 and y going from x to 2x. All right. And then C is the boundary. So it's very helpful just to do a quick drawing of this D. All right. X goes from 0 to 2. Now y ranges from x to 2x. So let's draw the line y equals x. Okay, this is the line y equals x. And then we have, above that, we have y is equal to 2x. And of course, I just as usual, the y equals 2x is going to look like this. All right. So, and then x goes from 0 to 2. God, I'm so terrible at that. All right. So this is this triangle region here. X going from 0 to 2, y going from x to 2x. That's the region D. C is the boundary in a clockwise position, going this way, and then down this way. That's what C is, the boundary of it. All right. Okay. So let's first of all put what Green's theorem is. This is going to equal basically the double integral over our region D of, let's see, this is P up here and this is Q. From our, so it's going to be dq dx, right? Yep. Minus dp dy, and then we do dA of that. We do a double integral. All right. So be sure, of course, that you have that formula handy so you don't mess that up. So in this case, what is dq dx? Well, q is equal to 2x squared y. So its derivative with respect to x is going to be what? Isn't it going to be 4xy with respect to x? dp is equal to xy squared. So dp dy is going to be what? 2xy. and we subtract that from the top one. So we have 4xy minus 2xy. Well, that difference then is a 2xy, all right? Okay, so we have this double integral over d now of 2xy dA. So Green's theorem converts this line integral into this double integral like this, all right? Okay, so as with any double integral, we have to then put it as an iterated integral. All right, and that is where the little drawing can help you from getting messed up. And let me tell you, for the one problem on the test that you have with similar kind of triangle, trust me, if you don't do a rough sketch of it carefully, you're going to end up with the wrong region. So make sure that it's just a little triangle thing, but make sure that you've got the correct triangle, and it's not too hard. It's just a matter of being careful. All right, so let's see here. Well, we're going to want to integrate this way, right? Up like this first, vertically, with respect to y. Okay, so that's going to be 2xy with respect to y. Now, what's our lower and upper for y? Our lower one is y equals x. Our upper one is y equals 2x, right? Okay, so y equals x to y equals 2x. And then our outer integral is going to be with respect to x, and that's going to go from 0 to 2. Right? Okay. And I'll just go a little way with this, and then I think we can all just figure out the rest of it. So therefore, now we do the inside integral first. What's that antiderivative going to be with respect to y? Yeah, xy squared. And then the bottom y is y equals x, y equals 2x on top. Outer is 0 to 2 dx. And then I'll plug this in and stop. So the top one is 2x. I'm squaring that, so that's going to be x times 4x squared on top. The bottom one is y equals x, so that's x times x squared. And that's from 0 to 2 dx. And I don't think we need to go any further. What is the final answer? The final answer is the number 12. Okay, that's the final answer. Here. Let's look at this. Well, yes.
I didn't really ask any takers very separate and integral. If you have the same thing but one's positive and one's negative, do they cross out?
Okay. In other words, you do those partial integrals. Is that what you're talking about? And you've got, let's just put as an example, one f is equal, say, minus sine of x. The other f that you come up with is a positive sine of x. No. Then if assuming you did the calculations correctly, it would not be conservative. When you're saying, are you saying that this minus and plus would cancel each other out? Yeah, okay. interaction between this and this?
These are separate, so this one's,
Okay, wait a minute, so we're trying to, I don't understand. You're trying to find this isn't a vector, what? Let's just cut to the chase. If this one, it's number 4. Okay. All right. So you're saying you found out that you're saying you didn't get it. Let's do it. So you're saying you came up with not something a little bit different. Because it says here, show that it is a conservative vector field. And what did you come up with?
negative, so I didn't know if they crossed each other out.
No. You must, let me work it then. And here, this is number 4. Take-home quiz 4. And I'll just do part of this thing. The field that we're given here is, well, wait a minute. Okay, so the field that we're given is 1 plus xy times e to the xy, that's times I, plus e to the y plus x squared exy times j. And the first thing we're told to show it's conservative. All right. So doesn't that mean then this is our p and that's our q, right? We only have 2 dimensions here. So don't we show then that we need to show that the derivative of q with respect to x is equal to the derivative of p with respect to y, right? Okay. So what do we have here for the derivative of q with respect to x? Okay, that's going to go away because that's y. Now here, what do we need? What rule do we need to use here to get the derivative of that second term? Yeah, we have to use the product rule. Did you use the product rule there? Okay, all right. Of course, I'm sorry. So we have what? X squared times the derivative of exy. Y is our constant, so that's going to go down with the chain rule. So that's y e to the xy. And then we add the derivative of the first part, 2x times e to the xy. All right. So that's our dq dx. Does that agree with what you had? Okay. dp dy, we come up with, let's see. I think what I did on this is first of all, I just distributed this as e to the xy plus xy e to the xy. I think I did it like that. And then we do the derivative with respect to y. Well, this one, x is our constant, so that's x e to the xy. Is that right? Okay, yeah. And then, I'm hoping that's right. Yeah, okay, because we'll get another one. Okay, and then we have to do, okay, this is with respect to, y, so we have to do, again, the product rule with this one. So this is, let's say, plus xy times the derivative of e to the xy with respect to y. So that's going to give us another x down below, x e to the xy. All right, and then plus, now then the derivative of xy with respect to y, that's just an x times e to the xy. And we get the same thing on both sides. These two add up to this, that equals that. So we've shown it's conservative. Now your question then is finding the little f, right? You're having a problem with that. Okay, so that means that this part here, our little f with respect to x, has to equal 1 plus xy e to the xy. And our little f with respect to y has to equal e to the y plus x squared e to the xy, right? Okay. So we need to do the antiderivative of the first one with respect to x. And I think what I did here again is I think I went on and just distributed and then went on and did it. So 1, so that's e to the xy plus xy e to the xy. Okay, this is with respect to x. So first of all, what am I going to get for that first term? Yeah, 1 over y, because y is a constant. 1 over y times e to the xy, all right? And now for this one, oh yes, oh yes, oh that's right, the integration by parts is needed. All right, you got me into it. So, because notice here, y is constant, but we have x e to the xy, so unless you're using some kind of table, we need to do integration by parts. Okay, so what am I going to let my u equal here for integration by parts?
xy.
Yeah, I think that's right. Let u equal xy. So du is going to be equal to, this is with respect to x. So du is what? Y dx, right? Okay. And then dv is equal to the rest of it, e to the xy dx. So now we do the antiderivative with respect to x. And what do I get with that one then? Yeah, again, 1 over y, e to the xy. Okay. So remember here, so it's u times v minus v du. So u times v is going to be, u is xy, v is 1 over y, e to the xy, minus integral of v du. Well, v is 1 over y, e to the xy. Du is y times dx, all right? So what we have y's that are canceling out here, so this gives us x, e to the xy, minus the y's are constant here, they're going to cancel out anyway, and so this is going to become what? Again, integral of e to the xy with respect to x is going to be 1 over y, e to the xy. Oh, I see what you're saying. No, of course, in this case, they would cancel each other out. Then, so what we had here then, remember this very first term where we didn't have to use the product rule, that got us 1 over y, e to the xy. The rest of it, though, what we get here is plus the rest of this, and this is our little f function. And now we could also have tacked onto this.
Well, you still have another integral, but
Yeah. Right. Well, this would be we could have tacked onto this some function just of y, right? Because y was our constant. Absolutely, Jenna. In this case, as part of our little f, we have two things that do cancel each other out. Right. So we're left with x e to the xy, plus we could have some other little g of y hanging on. All right.
another integral to integrate this out.
Right. So guys, this is only part of it. The next one is then handling the fy and doing the antiderivative of fy. All right. Oh, I guess that puts us at the end here then with this. Those were all good questions. Okay. So again, put down all these formulas here, but also recognize when you have to use them. Okay, just the formula won't be good enough, and you'll just be tucking those in with your tests. So when you hand them in, all right. So I don't, just so that I don't know, just just so that I don't see that you didn't microfilm the whole book and then used and I saw you using a magnifying glass to go through your notes, all right? Okay, so I'll see you on Friday.
Just to check, imagine the fact that we have these, we're going to have these equations to make the test.
No.
Okay.
No, I'm not pulling that.
Okay, so as in the past, it's going to be substantially the same as the take-home. So as in the past, it's going to be substantially the same as the take-home test. I mean.
Okay. Oh, yeah, I did tell you guys earlier, you may not have been here that day, that the best way to prepare for this test on Friday is the take-home test and the review test.
Okay.
Yeah.
Since in the past, like, the test, like, I've done pretty well with the take-home test, so I just wanted to make sure that.
Well, check out the review set too.
Okay, right. I mean, okay. All right. Thank you.